Well, this is Benford's law, and it's about numbers, but it's about the leading digit. For example, you could look at the populations of all the countries in the world and look at the leading digits of all those. So, for example, if it was 1,269, then the leading digit in that case is the 1. Benford's law works on a distribution of numbers if that distribution spans quite a few orders of magnitude. And the brilliant thing about populations of countries is it actually goes from tens up to billions. If you were to think about that, okay, what are the distribution of leading digits? So some of the populations will start with a 1, some will start with a 2, 3, 4, 5, 6, 7, 8, or 9. And so there are 9 possible leading digits. And you might imagine that each one of those possible leading digits are equally likely to appear. So that's 1 in 9, 11%. And if I was to plot that on a graph, you might expect that to fluctuate around 11%. So it's going to sort of, go like that. So what actually happens is that a third of the time, that's up here, right? A third of the time, the number you choose will start with a 1. And it will hardly ever start with a 9. So 9's kind of like down here, tiny number. And then you get this brilliant curve that goes up like that. Isn't that crazy?
I know you talk about this sometimes in talks and things you do. What's the reaction to that normally when you tell people this?
The reaction, okay, the noise is sort of like this. And there's a certain amount of disbelief sometimes as well. The way we do it actually in the show is that we get people to tweet numbers to us. So we're collecting numbers and I try to give them ideas. So maybe like take the distance from the venue to where they live and convert that into some strange units or something like that. The interesting thing is, like I was saying, it works so long as the distribution you're choosing from spans loads of orders of magnitude. But if you're picking numbers from lots of different distributions, the individual distributions don't have to span lots of orders of magnitude. The meta distribution of individual things picked from different distributions follows Benford's law anyway. So it works brilliantly well.
What clump of numbers will this not work for?
Human height in meters. So humans are between 1 meter and 3 meters tall. So it doesn't work for that. You get a massive load around there, and no one's 9 meters tall. Anything that has that kind of short distribution, it doesn't work for. But it does work for several distributions put together that don't necessarily individually follow the rule. So I did it for populations. I did it for areas of countries in kilometers squared. If you take one number and convert it to loads of different units, that will tend to follow Benford's law as well. You can do it for the Financial Times. So look at all the numbers on the front cover of the Financial Times. They will tend to follow Benford's law as well.
Just a quick interjection, you can also apply this to the number of times you watch Numberphile videos or leave comments underneath. More information at the end of the video.
So the explanation is to do with scale invariance, which I'm just getting my head around now, but there are a couple of intuitive ways of understanding it. One of them is to use the idea of a raffle. To begin with, it's a very small raffle, okay? So there are only 2 tickets in this raffle. What are the chances of the winning ticket in this raffle having a leading digit of 1? Well, that's this one, so it's 1 in 2, it's 50%. But then if you increase the size of the raffle, so there are now 3 tickets in the raffle. The chances now are 1 in 3, or about 33%. If you add a 4th ticket, then the probability of the leading digit of the winning ticket being a 1 is now 25%, and then 20%, and so on, until you have a raffle with 9 tickets in it. And then the probability of the winning ticket having a leading digit of 1 is 1 in 9. It's 11%, which was the kind of intuitive thing that you might think. But then you add your 10th ticket. And now there are 2 tickets that start with a 1. So now the probability is 2 in 10, or 1 in 5. So we go back up to 20%. The probability will go up and up and up as you add more tickets that start with a 1. And once you have a raffle with 19 tickets in it, you're up to something like 58%. And then you add the 20th ticket, and so the probability goes down again. So the probability of the winning ticket having a leading digit of 1 will go down and down and down through the 20s. It will go down through the 40s, down through the 50s, 60s, 70s, 80s, 90s, until you add the 100th ticket. And then the probability will start to go up again. And the probability will go up and up and up and up all the way through the hundreds. And then you get to the 200s, and it goes down and down and down through all the 200s, 300s, 400s, 500s, 600s, 700s, 800s, 900s. And you'll be back to 11% again then. And then you add the 1,000th ticket. The probability will start to go up again. So the probability goes up and up and up through the thousands. And then down through the 2,000s, 3,500, blah, blah, blah. And then you get to 10,000, it goes up. And so basically the probability of the winning ticket having a leading digit of 1 fluctuates as the size of the raffle increases. And so this is a log scale of the raffle increasing in size. So you might have 10, 100, 1,000, 10,000 and so on. And then this is the probability here of the ticket having a leading digit of 1. It will sort of go... it sort of goes like that. What Frank Benford realized was that if you pick a number from a distribution that spans loads of orders of magnitude, or if you pick a number from the world and you don't necessarily know what the distribution is in advance, then it's like picking a ticket from a raffle when you don't know the size of the raffle. So you have to take the average of this wiggly line, which is what he did. So that's the average there, and it's around 30%. There's a formula for it, which is the probability of picking a number with a particular leading digit of d is equal to log to base 10 of 1 plus 1 over d, like that. And so that's how you do it. And if you plug 1 into there, then it's log to base 10 of 2, and it ends up being about 30%. The beauty is that you can do it in any base. So this doesn't have to be base 10, it could be base 5, base 16, whatever you want to do. And so you can apply Benford's law to different bases. This is a formula that they use, a forensic accountant would use, so tax fraud or something like that. If you're making up numbers in your accounts and the numbers you make up don't follow Benford's law, then that's a clue that you might be cheating. So this is a number this is a formula you need to remember if you're going to cheat on your tax return.
A lot of things that sort of mathematically inclined people like yourself tell me when I hear about them sort of seem counterintuitive, and then you cleverly explain why it works the way it works. This is one of the few things that when I've heard about it, this just seems logical to me. Like when someone says 1 will come up more often, to me that just seems like, of course that would happen.
Yes, funny, isn't it? Some people are like you. I would say you're in the minority of people that go, oh yeah, obviously. And I wonder if there is another sort of intuitive way of looking at it that you've tapped into, which is that if you imagine something like the NASDAQ index or something like that, and I don't know what the NASDAQ index is size-wise, but imagine that it's the NASDAQ index is at 1,000. To change that to 2,000, you would have to double it. So the NASDAQ index would have to increase by 100% to get from something that starts with a 1 to something that starts with a 2. So that's quite a big change. But if the NASDAQ index was on 9,000 and you wanted to increase it to 10,000, then that's an 11% increase. So it's hardly anything. So basically, you don't really hang around the 9s. As things are growing and shrinking, you don't hang around, whereas you do hang around the 1s. And maybe that's intuitive to you, and so you're like, yeah, obviously.
If you'd like to see even more about Benford's law, we've done a bit of a statistical analysis to find out whether or not your viewing habits and the number of times you comment on Numberphile videos is following the Benford curve. The link is below this video or here on the screen, so why don't you check it out.